Hello. So what I want to talk about in this module is software testing. So let me just start out by saying, just very important point. If you're not testing your software, you don't have working software. Your software is riddled with bugs. And that's not a reflection on your coding. That is just simply a reflection about the nature of coding, which is that it's incredibly difficult. And we humans just can't keep all those details straight. So we're going to make mistakes. I personally don't think I've ever written a single program, no matter how short, that worked the first time. I had to test it to get it to work. So let's just take that as a fact. We need to be able to test. And so now how do we test? Okay. So the first thing that I want you to know about is something called unit testing. And unit testing is about testing each function separately, right? So that you know that this function works. It works best when you kind of do the unit testing as you develop your code. So you write a function, you write the unit test for it, and then you actually test that function, and then you move on to writing the next function. So when you're writing the next function, you're assured that the first function you wrote is actually working. And what that means is that if you find a new bug, it's probably in the new function that you just written, so that it never gets away from you. Now, the kind of testing that we do for unit testing is we actually call our function and we pass it a given argument. Like here, let's say I write a square root function, so I'm going to test it with the number 4, and I make sure that it has the expected output, which is 2. There are other kinds of testing, okay? So for example, we have regression testing. And I think of regression testing as what keeps me from being really embarrassed in front of customers. So I put out a version of the software, and I do my best effort. I test it. I think it works. I send it out, but the customer sent back a bug report and said, oops, we found a problem. So for example, here, the customer may have discovered that square root of 37 is actually returning, let's say is returning 12, okay? And this is clearly not the right answer. There's something went wrong in my code. I tested it for 4. I failed when it ran for 37. So I try to figure out the bug. I fix the bug. And now what I do is I add this to from my unit test suite. So my unit testing will say square root of 37 should be equal to 6 point whatever it is, okay? So the point is that I add that to my test suite. That's what regression is about. If I make a change to my software tomorrow, then I simply rerun my test suite and I make sure that any bugs that I had already fixed don't reappear, okay? Which, like I said, is a very, very kind of an embarrassing situation where the customer says, hey, aren't you even trying, okay? Now, another type of testing that you'll hear about a lot is called mock testing. And the idea with mock testing is this. Let's say that I have two functions, f and g, and f calls g in order to do its job, okay? Well, the problem is that when I'm testing f, essentially I'm also testing g at the same time. And in unit testing, I want to be able to test functions completely in isolation. So one of the ways to do this is to replace g with another function. Let's call it mock g, okay? And what mock g does is it simply returns kind of a hard-coded value, for example. So let's say that mock g is supposed to find the area of some polygon. Mock g can just always return the area is 3, okay? And then we use that in f. And that way, if I find an error, I know that it's not in my area finding routine. It's got to be just in f, okay? So that's what mock testing is about. It's just a way to make it easier to do unit testing, okay? Now, random testing is actually a pretty promising idea. And what I want to do is I want to be able to test not just, let's say I have 100 unit cases. That's nice, but wouldn't it be nice to test the software in 100,000 cases instead? So what we'll do is we'll randomly pick a number. Let's say that I pick some x, which is greater than or equal to 0, okay? I randomly pick x, and then I want to try to find the square root of x, okay? Now, the problem with that is that I don't actually know what the square root of x is, right? And that's the function that I'm trying to test. So what I might do instead is find the square root of x squared. Okay. Now that I actually know that the answer should be x. Okay. So that's the way that random testing works. If there's some way for me to know the answer, what it should be, maybe that is because I have a slow version of the routine. Okay. And I'm actually testing a fast version of the routine. I can actually just randomly generate inputs, use the slow version to get the right answer, and then make sure that my fast version of the routine computes the same value, right? So that's what random testing is. it's really a great idea, whenever we can use it. Okay. And finally, is something that's related to it, and it's the idea of little theories. And little theories are really, really, really important. So with a little theory, what I have is this is some property that I believe is true of my function. For example, if I have the function square root of x, I'm pretty sure that square root of x is always greater than 0, right? So that is a little theory. Okay. So I can just run it with any random input. I don't check to see that I got the right answer. I just check to see that it has this one property that I can test. It's greater than or equal to 0. I might have some other thing, like for example, square root of x is greater than square root of y if x is greater than y. Okay. Again, that is a little theory. And what I can do is I can generate random inputs, get their square roots, right? And then check to make sure that the less than relationship is preserved by square root. What other theories might I have? Well, I might have the square root of x times y is equal to the square root of x times the square root of y. That's another property that I expect my square root function to work. And as you can see, I can just build as many of these as I want. And they don't give me an absolute assurance that my function works correctly. But if any one of these is violated, then other my function actually doesn't work, right? So it's good for testing. And then if I can run this for 100,000 inputs, then I feel pretty good that my function is probably correct. Okay, now one thing I want to tell you is that actually we have lots and lots of testing frameworks, okay? And the very, one of the great early testing frameworks that influenced a lot of folks is this one right here, which is JUnit, okay? JUnit is really kind of changed the way that programmers think about testing. It's a great, great framework. If you're using C++ or C#, then you got some testing frameworks you can use. Swift is a relatively new language, and we have XCTest that works fairly well. Python has something called unit test, and as you can tell, it's just a unit testing framework, similar in style at least to JUnit. Okay, but here's what we care about. We need to have unit testing, okay? And remember what this is. This is test to the form f of x is equal to y, okay? Where this is known and that's known, right? So you pass in a known input argument and you know what the result should be, so you can check to make sure that you got the right answer, okay? Assertions are also important. This might look like assert I is greater than or equal to 0 and I is less than n, okay? So if I try to find some index I that has a value that I'm looking for, I can actually add an assertion that says, oh, and I found it in the code. So what's really nice about assertions is this. I, as a programmer, I'm making this assumption, right? I believe that this is true. So if it turns out that it isn't true, okay, my code will break later on. And I don't know how far it's going to take for it to break. It may be 10 steps later, it may be 100 steps later. By putting the assertion, what I'm making sure of is that as soon as this assumption is violated, then I get to know about it. So if I get, oh, I is actually outside of that range, then I go, oh, that can't be right. And I'll look and I'll find the bug in the location that I have, right? We also have to have little theories. And like I said, little theories are just a sanity check. So they let me go back and make sure that some assumption I'm making about the code, like square root is always non-negative, are actually true, right? And again, that doesn't mean that the square root function is working, but at least it does mean that that is not grossly violating some assumption, okay? And randomized inputs are very nice to have. They're not crucial, but they're really nice to have, especially in conjunction with little theories, but even in conjunction with other things, if there's some alternate way to test, okay? All right, now let's just do a simple example, okay? And this is supposed to be reminiscent of sorting, right? So you may have seen Quicksort, and what we have in Quicksort is that we take some array A, and then what we return is actually three things that are kind of combined. So we return the partition low after we sort it, so I'll call Quicksort on that, okay? And we'll append to that partition equal, and also sorted version of, I guess I should say QS of partition high. Okay, so now what are these partitions? Well, what we do is we just pick some element k, right? And partition low has all the elements that are less than k. Partition equal has, well, just k in it. And partition high has all the elements that are greater than k. So when I sort this array, well, the small ones comes first, right? You know, those are the ones that should be first. Then we have the ones that are equal to k, then the ones that are larger than k. The important thing is that these are sorted, right? So that's kind of a nice, in fact, it's probably the version of sort that you use when you sort files in your computer, for example. Okay. Now, let's say that I write those 3 partition routines, and that's really the hard part of this sorting algorithm. So how do we know that they're right? Okay, and that is a hard question. So here's what I can do to do the to check it, right? So here is my unit tests, right? So in my unit test, all 3 of these, you notice that what I'm doing is I'm giving an input array, right? This is an input, and then I have a known output. Okay, so that's the reason that unit tests have a tendency to be rare, because I actually need to have lots and lots of examples, right? I mean, each example is a different unit test. So that's what's hard about these, right? You know, you develop those as time goes on. In the meantime, I can use something like little theories. Okay, now look what the little theories let me do. I'm going to take my functions, right? And if you look at this first one, all I'm doing is just making sure that I'm not losing any elements, right? So I take the length of my partition, or rather length of my array, right here. And initially, let's say that my array has 10 elements, okay? Well, there's 1 here, right? Maybe there are going to be 3 that are low. Oops, I'm sorry, this should be high, right? I have 3 where the partition is actually that are bigger than k, and then I must have 6 here, right? Because they have to add up to 10. So that's my little theory. It's just simply that if I take all the ones that are smaller, you know, the number of those that are equal to, and the number of those that are larger, what I should get is the total number of elements, right? What else should I know? Well, let's say that I take the maximum of all of the small numbers. Well, that maximum has to be less than k in partition low, right? The minimum of partition high, it has to be greater than k. Again, those are just little theories, right? Now, if I look at the partition equal, both the minimum and the maximum should be equal to each other and should be equal to k, because that's how the partition is supposed to work. So all of these are just simply things that I expect to be true no matter how the partition code is implemented, and also no matter how the array looks like, right? It could be randomly generated array. I expect all those properties to hold. That's what makes it a little theory. Okay, now I just want you to always realize that little theories do not guarantee that the software works. You can have a little theory, run it for 1 million random inputs. It's easy to do, right? And you wait 10 minutes for the program to finish or 20 minutes for the program to finish. You still don't have a guarantee that it actually works. And so, so here's a little theory, right? But we may have to add more things to that to actually completely cover it. So an example of that might be, let's take the partition, append to that the equal partition, append to that the greater partition, right? And what I should get is a permutation of the original input, right? So what does permutation mean? It means that it has the exact same elements and the exact number of times. So I've checked the length. I haven't checked that I have the same elements. My partition function could, for example, return 0 elements, right? It could be that equal just returns 10 0 elements, and low and high always return empty, right? So it would pass my unit tests, but it certainly wouldn't be correct. Okay.